Yeah, if you notice, there's a lot of research in the industry that shows this is an example of research from and a report from the New York Times about the impact that stories can have on our lives, and more importantly, on our children. And it's that position that the entity that funds FamilySearch takes. It's all about families and how to improve a child's chances of succeeding in this life. FamilySearch is funded by the LDS Church, and it's a nonprofit, meaning we don't have the luxury of charging for our services and then taking that revenue and reinvesting it into the organization. Today I'm going to talk to you mainly about this third subject, replacing a relational database and then migrating to a cloud-hosted project, cloud-hosted platform for our project. I'm going to summarize a couple of the important architecture and design challenges that we ran into, and then show you that the results bear out the effort that we had made to make the switch. I had meant to spend a little bit of time showing you the user interface. Since it's free, you can go generate an account, log in, and explore the interface yourself. I would just note that there's several applications, the family tree, memories, indexing, which takes a photo of a historical document and allows a crowdsourced model to turn it into a digitized textual representation that we can put in our Solar Search system. But one of the things that you ought to be aware of is the fact that it's big data we're talking about. Not so big as maybe on a Netflix scale, but huge data. In the records collection for our historical records, there's about 6.2 billion records. 1.25 billion images that are online, and web views a day, 11.2 billion. Family tree application is shown in these screenshots. I'm not going to spend very much time talking about them, but only to give you a bit of a taste to be able to move through and try it out for yourself. Again, it's free for anybody in the world to use. There's a possibility that you may run into a historical record that we license from a third party, and that third party puts up a paywall on you, but you will never see a paywall from FamilySearch. Let me move to the statistics so you get a feel for the tree application part of FamilySearch. We have just shy of 1.2 billion persons represented in the tree. We have about 400,000 or so persons added to the tree a month by users. In the source service that we use, sources define the existence of people that have been here on the earth. We have about a billion, slightly shy of a billion sources right now. And sources that are added to a person, or in other words, if you get a source and you want to say this source is about this person, we call that a source attachment, and there's about 1.28 billion attachments to the tree. So what does the system look like? Well, I took a screenshot of our App Dynamics project console page, and this is it. You see it in all its glory. Unfortunately, it's hard to reason about that type of a view of the system. It has tens of services, many tens of services. It has thousands of nodes. It has hundreds of database servers, licenses on those servers. Many deployment and development teams. We operate in a continuous integration, continuous delivery way, and we have budget events just like everyone else. And one of those budget events I've illustrated by this slide. And it's essentially, you can probably even still hear the reverberations of our Oracle representative. They're in California, we're in Utah. You could definitely hear the echoes clear across the mountain ranges and through the canyons that said, it'll probably take them 10 years and a miracle or a set of miracles to get off of our product. And so one of those budget events was that our maintenance license was coming due. And we had to negotiate and work out a moving forward strategy. Well, that moving strategy eventually was we need to replace the commercial database product. And we need to do one of two things. Go to either an open source relational database product, or we need to be able to substitute a different technology like a NoSQL database where it made sense and was appropriate. And so one of the things that we did is we followed some of the counsel to create and identify the quality attributes that we were most interested in as we made this transition. And we built this utility tree, and ultimately we arrived at this prioritized list of quality attributes, security being number one, in that we operate throughout the globe under all of the government regulations of whatever area or region we're talking about. And so in the US, that's HIPAA law, EU regulations, of course, in the EU, etc. There's an additional, if you will, current to this project, and that is when we were originally planning it, we could see the end date of the maximum capacity of our commodity database servers that we had the database running on, and the performance and capability that we would get. And this differential here wasn't enough to sustain the growth that we were seeing at the time. So we actually had to come up with a contingency plan, which is this step function, where we would take our disaster backup copy of the database and database server, we'd put it in a read-only replica service, and we would pipe a lot of our read-only transactions to it so that we could have more time if needed. Our target, though, to get off of the Oracle database was also driven by this capacity constraint that we were seeing. Of course, the dotted line is the model of the capacity consumption that we were having throughout time. So we did the normal thing. We built a Gantt chart with essentially the services that we needed to work on, and we projected out and estimated what it would take to get it done. And you can see the final delivery date was out here, Q1 of 2017. But the thing that drove the thinking around it was this Tree Foundation service. Tree Foundation service was delivering Q4 of 2016. And if you remember from the previous slide, we were going to run out of capacity early Q1 2016. And therefore, we had to do the thing that nobody should ever do in their lives. We had to scrunch the schedule. We had to contract the schedule so that we could deliver the project sooner. Well, Fred Brooks would agree with me that when you do that, you'd never deliver the project sooner. But our objective was to pull in that Tree Foundation module. This is basically the service and the database that runs the tree with that 1.2 billion persons in it. And we needed it to come in early, or as early as we could. We compressed it down, but also drove out some of these other concerns. Now, I've tried to keep the time schedule, the time scale on the this slide and the previous slide the same so that you could compare. The one before was this, and the one after was this. Well, we pulled the schedule in, and we started operating against the topics that we had identified we needed to work on. And then we did what no self-respecting architect would ever allow happen to do. We also adopted more scope. And the more scope is illustrated in this slide by this Amazon cloud environment. We decided that it was appropriate for us to make the jump from an on-premise data center, we leased that data center, of course, to a cloud-hosted environment in Amazon. And we drew a bunch of pictures like this, and we drew special ETL kinds of concerns that we needed to keep track of, functionality over here that was going to be replaced by other Amazon technologies, and you get the picture. There's a whole suite of these diagrams to deal with all of the concerns of all of the services that we have in the website. So, what did we learn? What are the things that we might have paid attention to a little more closely if we would have but known that they were going to present the problems and the challenges that they were going to? The first is that the performance of our technology swap was interesting, and there were quite significant differences for us. On the relational side, we got very used to running parallelized query execution, meaning you have a huge query, it's running against a giant table, and you've got hints in that query that allow it to effectively use all of the CPUs and all of the partitions of data that you have in the database. The queries run a lot faster when you do that to your database. But if you end up with a technology that doesn't support that same type of functionality, your performance can be impacted. And we saw that in many cases in our application. We also were used to getting rid of an index or two that were causing us a problem and rebuilding them in a fairly short order through a parallelized index building approach. And that we didn't have in our relational technology, our open source relational technology. And actually we didn't get this till about 6 months after we had cut over. We also found that there were some queries that, based on the replication stage that we were, the replication mechanisms that we were using, that we were causing some queries not to be able to complete because the replication would come in and interrupt those queries from running. Now, on the NoSQL side of the business, we didn't have a very good appreciation about the operation and maintenance burden that it was going to put on the teams that were adopting it. If we had known these things or had more time to deal with them, we of course would have come up with better solutions than we came up with. I'm going to actually take you into a gory detail about this and related issues in just one moment. The next thing that we ran into are the weak transactional semantics that you find in the NoSQL technology that we purchased or licensed to run. In fact, we ended up having to combine some patterns, some industry patterns, to be able to deal with the weak transactional semantics that there were. And these three patterns here were the most important in the work that we did. Event sourcing essentially means representing the changes to your data in your database by a stream of events or a stream of changes that sum up to the total change that you're making. The commutative replicated data type essentially teaches you about being able to replicate data on nodes in the network and being able to update them and manage that data independently. And then finally, the command query responsibility segregation, CQRS, allowed us to deal with the data representation in the domain in a bit of a different way than we had traditionally thought about it in a relational database. Excuse me. So here's an ugly slide. You're not meant to grok all of it. If you draw a line right down the middle, you see the separation between our command processing and our query processing here on your right-hand side. Essentially, what we built was a mechanism that takes a request from a user, turns that into a command. That command then gets written into a journal storage set of tables. And then those the journal entries are summed into views of the data, where one journal entry might apply to several different views. And so through an entry in the journal table, we might update, 10 or 12 different entities in the views. The query side of things leveraged those views and those journal entries, took a view, read any outstanding journal entries that had not been applied to that view, applied the data changes of those journal entries, and ultimately represented the response back to the user. We did that, again, because, one, we need to have the transactional semantics or at least the pseudo-transactional processing that this gave us. And we also wanted to have a very wiki-like change history on the data as it's being changed, because our data model is primarily an open edit data model where anyone coming to the application that we can authenticate and authorize can view public data and can change it, anyone. So you can imagine you need a recovery model that's akin to the Wikipedia recovery model when somebody starts going and trying to destroy Wikipedia. When somebody comes and starts trying to destroy the tree, we need to be able to come back to the journals and recreate the tree back to a state and time that we deem as appropriate. The third thing we had to do is represented in this diagram, and it's all about getting this blue stuff, which are the services I showed you on that original ugly App Dynamics view that are running in production, into production in a secure way. Everything else around these purple services is platform kind of stuff that we built around the Amazon cloud to allow developers to specify what they want, need, and have to access in a file called a blueprint, which is basically just a document containing a JSON structure of data that's metadata about these services and how they interact and the information that they can send and exchange with each other. This turns out to be one of the primary pieces of magic that occurred in our organization. It abstracts almost every detail about being on a cloud provider away from our development teams and engages them in what technologies do they need to solve their problems. I wish these three things that I've just shown you are 45-minute or hour and a half discussions in and of themselves. I wish I had more time to spend on them, but let's get to the results. We were trying to achieve a schedule objective. And what happened was We delivered the first production cutover about 16 months after the project launched. That was end of Q2 2016. We were targeting Q1 2016, so we actually for a quarter had to engage our contingency of a read-only replica. The complete replacement of all of the hundreds and hundreds of RDBMS licenses took a little more than 6 months additional time. We achieved our scalability of the tree database. We are now horizontally scalable, and this graph is meant to show you, this graphic is meant to show you that. The red is our calculated capacity. It transitions because we did things like change from SSD to EBS storage, changed the number of nodes in the cluster several times, updated to a more performant version of Cassandra, converted instance types from one type to another in AWS, and then again adjusted the nodes accordingly. We also accomplished our performance objectives. The cutover was essentially right here, and you can see times of the day in which we measured our performance were pretty much randomly scattered between half a second and up as high as 4.5 seconds. We pulled all of those down to below a half a second by the technology changes that we made, and got a much more consistent operation out of the system, even though it is a distributed system, a microservice-based approach. That automated platform that I told you about is doing its job. We average, this is a screenshot of a Splunk dashboard that shows some statistics about the platform, but we average about 250 check-ins, builds a day. Out of those 250, we deploy about 161 on them on average. We deploy in about 10 minutes on average, and then we have in the neighborhood of 2,000 auto-scale events a day. Auto-scale events a day are important because they help us save money, and then the rest is an example of how successful we have been at our continuous deployment, continuous integration type of development that we're doing on the family tree. So in summary, those echoes are now kind of dying off of. It's going to take a miracle because we have seen that the miracle occurred. We are extremely happy with where we're at. The horizontal scalability of the tree database itself is likely the very most important thing that we accomplished in this, although the thing that has the most value for us is saving the money that we would have paid to the vendor for support and maintenance and licensing if we continued on. That's the presentation I wanted to give you today, and I'd be happy to take a few questions.
Any questions from the audience? Yes.
So, I think you said did you choose Cassandra?
We did. The NoSQL option that's running our tree is Cassandra.
Okay.
Yes. And let me go back, and you can see in this slide here, we are currently running R4XLs as the instance type, and we're running 33 nodes with a replication factor of 3.
Okay.
It's taken more time of our development teams than we like to have them operate it, though, and manage it, go through this kind of life cycle. Yes.
So Oracle is very good in query joinings, right?
I apologize, I can't hear you.
Are you able to hear me? Okay. So Oracle is very good in performing query joinings, right? So in case of the Cassandra, how are you dealing with this?
Yes, what did you say about Oracle?
Oracle joining the tables.
Oh, joins on the tables.
Yeah.
We had, the benefit that we had is when we were using Oracle, we were using a blob approach. And the tables were essentially a pseudo key and then a blob. Now, we had a few columns in there, but they were more metadata about the row than they were row data. And so we had already dealt with the joining problem mainly in tables because we already had that problem in storing the data on a row in a blob. So it wasn't as problematic as you might think it would have been for us. Good question, though. I have go ahead.
Were there any other considerations than Cassandra that you looked at?
Yeah, we started out from the perspective that MongoDB was the game in town and would have to lose the job. We did some performance work and did our homework, and it took us a long time to develop that CQRS approach that you saw in that complicated slide. And through all of that process, we did demonstrate that we were able to scale better and get a bit more performance by choosing Cassandra rather than MongoDB. There were others that we selected, that we analyzed too, but yeah.
Okay,
Very
thank
good
you.
questions. Thank you.